panels to close the day. The first one is going to be moderated by Lauren Frederick of Element 84, and I'll have Lauren introduce her team. It's on the Silicon Dream, New Reality AI in Remote Sensing, or New Reality AI in Remote Sensing. And we could not have a panel without AI in it, and actually we could have had 10. So we're really grateful to Lauren for running this one. And then we're going to have the final panel will be moderated by Terry Bush on Into the Great Wide Open, what's been built, what are the possibilities, and where are we going. So I'm going to, without further ado, turn it over to Lauren to kick off the next panel.
You guys can come up. Hi, I'm Lauren Frederick, and I am the CTO of Element 84. Element 84 is a woman-owned professional services organization, and we do a lot of federal work. I've actually always been on a Fed project my entire time there, first with NASA and now with NOAA. I am going to introduce you now to our panel. We were supposed to have 5 today, but Manil, his flight got canceled last night, unfortunately, and he sends his regrets. So we'll start off with some intros. First, we have Dr. Carter Christopher.
Hello, everyone. I'm Carter Christopher. I'm with Oakridge National Laboratory. There, I lead the Human Dynamics Research section. So in that research organization of about 50 people, we try to answer questions about humans and the environment and infrastructure and how they all intersect to ideally protect more humans and protect the environment.
All right, thank you. Next, we have Everett Hinckley from the US Forest Service.
Good afternoon. I'm Everett Hinckley, the National Remote Sensing Program Manager for the Forest Service. And I got sucked into the AI machine learning vortex a couple years ago, looking at wildfire and how we could improve our response times there on geospatial data.
All right, and next is Joe Foster from NASA.
Hey, good afternoon, everybody. My name is Joe Foster. I'm the Cloud Computing Program Manager at NASA, so I live in the technology enabling arm of AI.
Okay, thanks, Joe. Manil is not here, like I said. And lastly, we have Dr. Mike Tischler.
Good afternoon. I'm the director of the National Geospatial Program at the US Geological Survey. I am an AI enthusiast, and I'm a rabid believer that our geospatial data can be better used by the AI community, both domestically and globally.
Great. So with that, we're going to be talking to the panel, asking some questions. We also have a QR code up in case anybody wants to enter a question. My colleague Zoe is going to be checking the questions, and we're going to be using that to kind of gauge if there's topics we should head to or if we should stop for audience questions. So please take advantage of that. I'll leave that up. And with that, the first thing I want to talk to our panel about is your current use of AI ML on geospatial data. So we want to have a real talk here. Where have you seen successes? Where have you seen challenges? And maybe is there something you tried and didn't work?
The Forest Service is not using AI machine learning actively. We are using it passively because it's built into some of the programs that we're using, some of the geospatial programs. But we're now just starting to explore use cases and understanding what the legal ramifications are and the policy implications as we move forward, so that we're using it safely and we're continuing to produce products that are dependable and reliable and trustworthy.
The US Geological Survey is are making a lot of uses of different AI and machine learning tools. One caveat I'll say is that the USGS is really broad. We have lots of ologists, ecologists, biologists, seismologists, geologists, volcanologists, every flavor of scientist you can imagine. So there's no way I can understand all of the applications. So I've seen some slideware for understanding fish species from cameras that are monitoring and forecasting stream flow and all sorts of different things. In the closer to home in my own program, I know that we're looking at how AI can help us better characterize a landform data set, which doesn't really exist. We have a point-based data set of named geographic features like summits and canyons and things, but they don't have boundaries. They don't have polygons that are ascribed to those. So if you want to know where Pikes Peak is, we have a summit, a point, but we don't necessarily have a polygon that defines it. What we do have are 130 years worth of historical maps with labeled points that cartographers have put on there. So we've got an active effort right now, partnered with JPL, to help us figure out how they can automatically, using AI, infer where those label texts are and come up with sort of a geospatial boundary of where that summit is. And there are some challenges to it, like some of these maps are quite old and they were made by actual humans, not computers. So the labels are sinuous, they're turned upside down, they're long, they're thin, they're different font sizes, and different scales of maps. Some of the AI software doesn't recognize different orientations. They're used to reading text from left to right, not that's in a curve. So that's been a challenge for us, is to figure out how we extract some of these labels off of these historical maps. A little bit more formally, out of the executive order that came out last November, December, there was a pilot project set up by the National Science Foundation, the National AI Research Resource Pilot, that was looking to better take advantage of federal AI resources, both data and compute, and expose that to academicians and other people that want to have an interest in using it. Initially, USGS was not part of that, but I'm happy to say we've contributed a number of our data sets, like the 3-depth data set you just heard about, so that if there is somebody that wants to have an AI application that's based on elevation data, now they have links to it through this pilot for free and can be combined with other resources that are there and offered by a number of other agencies, many of whom are probably represented here. I'll leave it there for now.
Sure. So I think for us at NASA, as you can imagine, very broad, very wide, lots of ologists and physicists at our org as well. So I would say that, so I've been at NASA 5.5 years. Prior to that, I was at the National Geospatial Intelligence Agency for a decade prior. And so in the last 5.5 years, we've had quite a number of what I would call tinker projects, right? There's been a lot of experimentation into a whole variety of different realms of AI across NASA. One of the things that we've struggled with is like how to really operationalize them, right? And so some of the examples of tinker projects, on our aeronautics side of the house, there's a ton of like autonomous drone research, right? Like, I know this is a very geospatially focused conference, but if you ever want a drone to deliver an Amazon package or a cup of Starbucks to your house someday, right? It's not going to be a human actually flying those drones in an urban environment. And so there's a lot of AI research around like autonomous drone traffic management as an example. I saw a proposal come across my desk actually 5 years ago to work on a computer vision project around predicting wildfire movement and when wildfires broke out using geospatial data. Actually, if Manil were here, he would bring up one, so I'll bring it up on his behalf. They actually have operationalized hurricane strength predictor. And so they actually have been able to accurately predict, what category a hurricane will become when they first see it on the map using remote sensing data. So that's pretty cool. And then to make it less about Earth in general, I'm sure everybody at this point has seen the James Webb Space Telescope. We've actually already started building the next one. The Nancy Grace Roman Space Telescope is going to be launching in early 2027. And it's going to be producing 20x the volume of data as the original one, 300 million megapixel images, which is about 15 terabytes of data per day. And so they've been investing very heavily in computer vision models to detect subtle dips in starlight and to have a machine be able to detect whether or not those dips in starlight indicate if there's exoplanets orbiting around the host star, how big those planets potentially are, if they're in the habitable zone, and whether or not the atmosphere composition is able to sustain life on it. So as you can imagine, pretty cool AI use cases. They're a long way off from being very accurate at this point, but they're investing very heavily in those kind of techniques today just because NASA is moving into the era of petabyte scale science, and you're going to have AI to enable a lot of this. So I'll pause there.
Okay, there's a lot that I can talk about at Oakridge. Again, we are, as Mike and Joe has stated, we're quite a diverse organization, so I won't be able to represent everything that we do, but I do know that AI is used at Oakridge in everything from nuclear science to environmental science and biology, And what I'll speak to is how we're using it in our geospatial science division. You heard Budu talk this morning about the LandScan program, and so that's where I'll start. AI is a critical component for how we produce our global population models. Tom talked about how all of our understanding of populations generally starts with survey data, and the Census Bureau is a great source for that population level information. But that's collected or at least presented to the public as information along administrative units. And our sponsors within the defense and intelligence community needs to understand, and broader U.S. government needs to understand where people are within the environment. And so the best way to understand where people are within the environment is to understand what the built infrastructure looks like. And the best way to map that at scale is using artificial intelligence. We've spent a long time, as Budu said, LandScan's been around for 25 years. We were not doing artificial intelligence to understand the built environment 25 years ago. But that capability has evolved to allow us to first understand where are human settlements writ large, and then ultimately, where are the buildings within the landscape? And then now, what kinds of buildings are we seeing within the landscape that we can then use to inform how many people might be occupying this building versus another building? So characterizing buildings at scale from satellite imagery is very much something that is feasible and doable, accomplishable today. It's what we're doing at Oakridge. Budu mentioned this morning our USA Structures work, which we're doing for FEMA, map the entire United States, 450 square feet and larger. And so those are critical elements for understanding the built environment to help us map populations. Today, though, we're evolving our approach to population modeling to be an entirely AI-driven approach, where before we're using AI to create derivative data sets that we could then fuse together using a model to estimate population for a given pixel, creating a gridded population data set. Tomorrow, actually this year, we will have our beta release of a global data set that is entirely AI-driven from an ensemble, a suite of ensemble machine learning models that is essentially recreating our historic data using dozens of inputs. And so we're kind of transitioning from a data fusion process to a AI-driven process that ultimately will allow us to get to use that phrase, the digital twin of the population in a much more, or to have that digital thread to be much more dynamic and less an annual delivery and more a iterative update in the places of the world that are changing. Some other things that we're doing from an AI perspective, NLP is really important for us when it comes to merging data sets together. So there's lots of great open data out there. We've talked a lot about it today, but it's all collected using different schemas. Everyone talks about the world in a different way, especially when you start collecting data from overseas locations, and things that we understand to be a supermarket are referenced as something else in different countries. And so there's the language translation problem, but there's also just the semantics challenge of being able to fuse all that data together. And so NLP is a huge benefit for us to be able to create knowledge graphs or semantic knowledge graphs to stitch these disparate ontologies together into a singular data set that we can then trace through and ultimately use to represent the world in one common framework. I posted on LinkedIn a couple of weeks ago about some work that we're doing on those derivatives that are coming out of our machine learning work, computer vision work. So taking a satellite image, creating building features or features of the built environment out of that satellite image, but now they're vectors, and I can do interesting things with those vectors based on the morphology of them, based on the shape, the size, the number of vertices that correspond to that building feature. And so we can create machine learning models, and we do create machine learning models that look at the morphology of the vector features and are able to help us characterize whether that building is residential or non-residential, or if it's non-residential, what's its function. We can look at other morphological indicators and infer building height and number of stories. And so there's lots of interesting derivatives on derivatives that we can, models that we can create. And so I can keep going on and on. There's a lot there. I certainly, Zoe asked about successes and challenges. Those are successes. There's plenty of challenges, and it takes a long time to kind of, to figure all of this out. Our goal at Oakridge is in many ways to fill a void from a data perspective for our federal government. There's lots of data needs. There's lots of needs to understand impacts of the environment or conflict on people and critical infrastructure. And so we're trying to create data sets at scale that help our government do that. And so AI is really important to that, but it takes a lot of work. And a lot of times these models are not transferable across geographies. When you work at a global scale, you find that you build something to help you model the situation in the United States, and it doesn't really work well in any overseas country. And so there's retraining, there's new training data that has to be collected, there's new parameters that have to be resolved for these models. And so there's lots of work to make these models work in all the places we need them to work. I'll pause there.
Thank you. So I want to jump over to Everett. So in your beginning your journey into AI, and I'm wondering kind of what you need to see, how are you prepping your team for that? What are you looking at to really jump into AI, and how do you plan to get started? Because I'm sure there's a lot of people in this room who aren't quite sure how they're going to start.
Yeah, thanks for that. And like I said, I got involved in AI and machine learning, at least thinking about it, roughly 2.5 years ago, looking at some wildland fire support applications. My role in fire is to assist with the remote sensing, reconnaissance, and product production over wildland fires. So over the past 20 years, we've developed a number of both classified and unclassified capabilities that allow us to do more rapid fire detection, better positional accuracy on new fire detects, more accurate mapping on active fires, the points, lines, and polygons for the active fire fronts, and burning points outside the lines of containment and things like that. And so we have more and more data coming at us all the time, and all of this data takes analysts sitting in front of screens looking at thermal imagery to help with the fire mapping, to produce a fire map for the teams to use at their 6 a.m. briefing. And I felt a number of years ago that the only way that we could deal with this in a manageable way to bring down costs and to reduce the latency, to reduce the subjectivity on fire mapping products was to bring in machine learning to do that same process. That's one of those low-hanging fruits that I see for fire mapping. Now you get into more complicated things like predictive fire behavior. How is the fire going to behave over the next 6, 12, 24 hours? That's a lot more, there's a lot more art and science in that process. And the Monte Carlo simulations on how a fire is going to behave fall apart pretty quickly. So I would like to be able to look forensically at past fires and see how those fires behave, looking at the fuels, the terrain, the weather, so that we can get a better understanding of the parameters that influence how a fire moves and behaves, and use that to do a better job of predicting the behavior on fires. So that's just the fire piece. You know, there's a lot more pieces in the Forest Service, resource management, land cover change, detection and mapping and things like that, but the fire was the thing that really grabbed me and said, this is going to be something that we can do.
For those of you who are using AI right now in all the various applications that you talked about, how are you validating what's coming out of your model, and how are we building trust in AI?
I can talk a little bit about that. We typically, since we're not AI experts, the few efforts that my own program is invested in, we partnered with experts who have their own criteria for validating whether it's F-score or something else like that. A good example is, Budu talked this morning about the stream problem. When you have a stream out there, of which there are millions across the country, and you're trying to determine how much and for how long water is in that stream. And why is that important? Well, there's this thing called the Clean Water Act, and the jurisdiction of the Clean Water Act changes based on the classification of the stream, whether it's intermittent or ephemeral or whatever other category you have. It would be nice to say, this stream has water in it for 176 days out of the year on average, and let the policymaker determine if the definition of ephemeral or intermittent fits based on the data. So we partnered with NASA and a couple of other experts around the world to figure out if they could come up with a model that was based on LiDAR, a year's worth of Planet and Maxar imagery over a small area, and a supervised data set. That's where the validation comes in, a supervised data set to figure out how closely they could get a match. It kind of worked, which was good, and we had some validation and some ground truth data to balance it against, and it kind of references the issue that Carter mentioned, that it worked great in our test area. It worked really kind of well, not great, in our test area in Idaho, Colorado, Montana. There's no way it would work in Florida or Arizona. And we knew that, so it's a step in the right direction. The other effort I talked about with looking at the landforms, that's a little more human in the loop, where we're trying to match and see if it makes sense. I don't know that we specifically have a criteria because we don't have a supervised data set. So that's something else we're learning ourselves as we go along.
So the traditional statistical approaches are a great place to start, looking at F-scores, precision and recall, and intersection over union, those kinds of things. But that typically works in the area where you've trained your model, right? It doesn't necessarily speak to reproducibility in other geographies. I think reproducibility is generally a challenge until, for anyone that's publishing open science, until we get to a point where training data is released with models and with detailed metadata on how everything was created and collected. We've, I think, matured. Josh spoke really well about it. We've matured in our approaches to geospatial metadata. We are not very mature at all in our approaches to machine learning metadata or machine learning model metadata. Metadata does not follow training data generally that we've seen. And so there's a lot of work to be done on the geospatial machine learning or GeoAI front with regard to standardization around metadata to ensure that we've got reproducibility and we can trust the data. When we seek to use data that was derived by someone else's AI, our first approach is just co-validation. Can we don't seek to create new buildings just for the sake of creating new buildings. We like to fill the gaps that exist out there. And so if Microsoft or Google or some other, even OpenStreetMap has great buildings over an area that we can use to model populations, we want to use that and not spend cycles creating an extra data set. But how do we understand whether that data is good or not? Even if it wasn't created by AI, I mean, if it's crowdsourced data, how do we know if it's good or not? And so we co-validate. We look for correspondence across all of those data sets. We look for alignment with our population models and understanding of whether we see what we would expect from quality and consistency and volume of infrastructure there. And so there's a lot of co-validation that goes on just to kind of sanity check the data to ensure that we can use it, and then we can feed it in. But we're placing a lot of trust in data that we don't have good metadata on. We don't know, in many cases, if you look at the Microsoft building footprints, you don't have good details on what imagery that was derived from. What's the vintage of it? And so in some cases, it's good is good enough, or good enough is good, however you want to phrase it, but there's always ways to get better around that.
So the standardization of metadata, do you think that's going to become less important with AI, since ideally you could just have metadata in different formats and AI will be able to understand it in the future, especially with developments with LLMs and stuff like that?
I would say yes, with specifically to your point about utilizing LLMs to help characterize, a disparate set of data to help normalize and standardize. I definitely think that's going to happen. I will also say, back to the previous question around, just what are we doing? What are some of the challenges? And all the same points that Mike and Carter made are true for us too, right? Around data sets and metadata standards. NASA has a TOPS initiative trying to get to transforming to open science. And as you can imagine, being a large disparate organization, we've, over the years, had a tradition of data hoarding, right? And so it makes it very hard to get some of this normalization of metadata or even sharing of data even into place. And so what we did about 3 years ago we went to our heliophysics community and said, hey, like there's this larger initiative to send, astronauts back to the moon in a sustainable way and have them there for a long time. And like understanding the effects of solar energetic particles from the sun's data is something that we really need to get our arms around. What are you guys doing? And we offered to have some data science generalists and AI generalists work with the actual domain experts. And as you can imagine, the heliophysicists were very resistant to this. They were like, oh, you guys don't know our domain. What could you possibly do? What could you possibly derive using just, basic data science techniques? And we said, okay, well, we're going to just go pull the archive since it's public data, and we're going to run 13 years of data from the Solar Dynamics Observatory through a couple of different AI models, and we're just going to see what the results are, and we'll give them to you to validate, right? And lo and behold, applying some novel techniques, they found, I think, thousands of previously undiscovered storms off of the sun, various other events, and they presented it back to the heliophysics community, and they validated that, like, okay, yep, these are all real. We didn't see these before. Clearly AI and whatever data science techniques you used for this worked. And so what it allowed us to do is sort of not break down some of those doors culturally, and they're much more open and willing to have cross-functional teams formed now. And it's gotten us out of this, like, well, you're not a heliophysicist, so you don't know what you're doing. And it has allowed us to partner more with, bringing in data scientists or AI experts in a particular field and have them as a generalist working with the domain experts in that area. And it's proven to be pretty valuable in a relatively short period of time.
So first, I completely misspoke. We do have a training data set for landforms, and I can't believe I missed that. Our research group has published that, so you're welcome to use it. To the metadata question, I think, yeah, standardization is one, and I think some key categories are going to have to be added. If you looked at the executive order that came out, there was a lot of discussion about the publication of synthetic data, and I think they even defined it as one that originates from an AI system, and that has to be captured in metadata to communicate to the user that this is indeed synthetic data. And I'd love to see things like, to the extent you can, what are the error bounds, and there's going to have to be things on how did you train this AI system. I think that is going to become really important for the transparency of the data set, for people to understand what was used, how was it trained, was it equitable, did you train data that's being used to predict storms in California on typhoons in India? It may not make sense, but that kind of thing I think really is important and does have to be communicated.
I just have one comment about metadata. Metadata in the Forest Service has always been kind of an afterthought. It's one of those things that people get to if they can get to it. But now that we're moving into this era of heavy use on artificial intelligence and machine learning, I think it puts extra emphasis on the need to have good metadata. All the way through the cycle, whether it's the synthetic data or the work that's been done prior to that, I think it adds emphasis to that fact that we need to have good metadata with all of our data sets.
And just maybe a final point on this, I think that I agree with Joe. I think LLMs, and as they mature, it will both streamline the creation of metadata, but also the ability to understand the utility of different data sets for different use cases, interpreting the metadata. Probably the biggest thing that I guess I'll pause there.
Okay, so we're here at FedGeoDay. So what do you think the role of federal agencies are in the growth of AI, and where do you see your agency in that?
I can start. I really believe agencies, at least my program within USGS, we can be great data providers. There's a desire out there, and you see this in a number of federal policies, a number of departmental policies for training data. Robust, well-described, large-scale, validated training data sets. The National Spatial Data Infrastructure community, of which Everett and I are a part, and you all may be as well, that's what we do. We make big data sets that are well described, that are validated, that are high quality. I don't think there's any reason why we can't add to that good quality training data sets, so that as people are going around testing or building or using these other, whether they're LLMs or other generative models or other AI systems, that it's based on data that can be reputable. I think that's a big gap and something that we can help fill.
Yeah, and I think from my perspective, I think the federal government has a responsibility to evaluate use cases, the proper use of AI and machine learning, and to help lead those efforts in divining those uses of the technology. And I had another thought there, but I think I lost it. So.
Yeah, I'll tag on to what Carter said earlier about getting the metadata with training sets and all that kind of stuff, right? So NASA actually took a step a couple of years ago, and they released the Science Policy Directive 41A, which requires all NASA grantees who take grant money from NASA to provide back both the training data sets, the models, the metadata, the algorithms, the software, the data used, like the everything, not just the output. So we've actually taken actionable steps of if you're going to accept data or accept grant money from NASA to do any kind of research, that we require the full corpus of data back as part of that process so we can validate what you've done. So was everybody happy about it? No. But we did at least take an actionable step to try to fix this part of the problem.
I guess I'll speak as a citizen and not a federal employee, since I'm not anymore. I think the opportunity space for the federal government, first and foremost, is opening its data so that the community can use it to create, to apply for AI problem sets. I think that that's some of the great work that NASA's been doing, opening up data. USGS is renowned for doing that as well. So I think that the more data that the community of scientists and engineers can get their hands on, the better. And so I think open data from the U.S. government is a key need.
And are there any ethical AI considerations that are affecting your work, how you're using AI, how you're thinking about it?
No ethics problems at all with AI. We're good there.
What are the ethical considerations?
Yeah, we have two large ones right now that we're struggling with, and one of them is less of an ethics and just more of an operational issue. But I'll start with the ethical one. There's a big push right now that LLMs are sort of all the rage, if you will, around how do you operationalize them again? Back to the get it out of the tinker project phase, and specifically around using LLMs to increase worker productivity. So doing everything from contract document generation, legal review, generating non-disclosure agreements, because those things all take time, and we've done a lot of process mapping internally to sort of see where are the bottlenecks, and it always comes down to legal review. And so it's okay, well, how can we accelerate some of these using LLMs, and then more specifically, well, who's validating the output of these, right, to make sure that it's not hallucinating? And so it's created some interesting paradigms around, at what level do you trust, at what level does it need to be validated? And then sort of on a sort of more operational side, we as an agency have traditionally done very big things, very big missions, right? Shuttles and rockets and, space satellites the size of school buses that we launch. And more and more, the industry, we feel, is moving in the opposite direction. It's we want smaller fleets of CubeSats, right? And the traditional ways that we've set up the infrastructure to manage our operations, you would need a fleet of people to manage a fleet of satellites, right? So it's well, how do you invest in AI then to control the fleet of satellites, and what challenges does that impose specifically? And so a common use case is okay, if we launch a fleet of Earth-observing CubeSats, right, and we're going to allow one CubeSat to tell the other CubeSat what it should look at next, how do you sort of cyber-proof or spoof-proof, or make sure the AI behaves responsibly and doesn't get tricked into doing something or tell the CubeSat behind it to do something, because in theory, again, you're not going to have a human in the loop. So there is some checks and balances on enabling full autonomy that I think are sort of a concern for us, and broader concern of should we do it, which is still kind of an open-ended question.
I'll chime in that the maps are generally made by the people in power, and yesterday's maps are today's training data. So there's concerns around representation in AI that I think we should think about. I don't know how we address that at this point in time, but it's something that we should be cognizant of as we source training data from existing or labels from existing data sets. One of the uses of AI that I think may help us at Oakridge on the on a particular problem that we seek to always be cognizant of is the issues of privacy. We spend a lot of time building data sets around where people are on the planet. And so there's certainly ethical concerns about releasing that data publicly, and how people can be protected in different parts of the world where the governments aren't as nice as they are in the United States. And so one of the things that we're investigating and doing more of with AI is the ability to create synthetic representations of populations, both the synthetic representations of characteristics, so kind of taking these characteristics that would be derived from census data and synthesizing them into unique forms that could be put into the environment that wouldn't be necessarily representative of individuals, but be representative of an average person or someone within a particular cohort. And then also using AI to generate synthetic activity patterns within a space so that we're not violating the privacy of anybody's particular movement. As Budu mentioned, right, all the tech companies have our movement data and our activity traces. We want to ensure in anything that we're doing from a research perspective is preserving all the individual's privacy. And so using AI to generate synthetic information that can be representative of what humans are actually doing in space, but not the exact pattern is a key piece for us.
I think there are two ethical considerations that I know USGS is struggling with. One, we're a science organization. We'd like to say we produced unbiased science for the world to inform decisions. And to do that, we have fundamental sciences practices that we subscribe to. We have a science publishing network that has very strict criteria when scientists want to publish. And I know a lot of scientists are concerned about how they represent in an academic journal article, a peer-reviewed publication, which AI system they used, what data it was trained on. That's something not just USGS, but I think the academia is struggling with. How do you characterize and communicate that, yes, you did use an AI system and what it was trained on? The other one I think is maybe more specific to mapping. At least I think it's more specific to mapping, or how I see it. We've earned a reputation for well over 100 years that when people see the USGS logo, they know it's reputable data. And you could say the same for Forest Service or NOAA or NASA or Oakridge or whoever. That's one of the beauties of our job, is that we're a legacy of providers of data that people know and trust. If we're going to start switching from a very human-in-the-loop system to one that's automated, or even automated that we don't completely understand, like AI, what's the responsibility to communicate that back to the public and make sure that they understand that, hey, this map was not necessarily produced by a well-described system. It was one that was produced by AI or included data that was synthetically generated by an AI system. It goes back to some of the metadata, but I think that's an ethical consideration that we're going to have to be confronted with. Maybe not this year, but if we start producing more data or more products from AI systems, I certainly want to be able to tell all of you as users how, when, where, and why AI was involved in the data that you're seeing.
Yeah, that made me think of Mike's comment. Made me think of the NEPA process, where we go out and evaluate different options for land management. 5 minutes, got it. Thanks, Doug. So that involves a lot of ologists looking at the landscape, understanding what the wildlife populations are and how the land's being used and so forth, and developing different options for how to use that land. And if we start taking the human out of that loop, how do we check, to make sure that there's ethical uses of the land going forward? Chris's comment also reminded me of two books that I had as an undergraduate: How to Lie with Maps and How to Lie with Statistics. So.
Okay, so I'm going to pivot over quickly to audience questions since we don't have a lot of time. So the first one is Carter. You mentioned using NLP to make knowledge graphs. Could you elaborate on that a little more?
Sure. So we have a platform at Oakridge that allows us to harvest open data from Wikimapia or OpenStreetMap or Flickr, whatever. Right? Pick a source. But our primary goal around that is to characterize points of interest on the planet. And as I mentioned earlier, Those points of interest are described uniquely by each unique source. The typical example could be a house of worship is described as maybe in the United States as a church, and that same place in another part of the world could be described as a mosque, or just maybe there's market and supermarket and grocery store. And so we have, our research engineers have developed NLP models that kind of break down the ontologies or the semantic ontologies of those unique data sets and ultimately stitch them together such that we can ultimately help with conflation and deduplicate duplicative points of interest, but also as edits are made to one particular source, we can kind of trace those through to edits in other sources.
Thank you. The next question is, there was a lot of discussion about air or space-based imagery for AI, but are any of your organizations using ground-based imagery with AI for validation?
I have a really good example of that. There's a network of towers out in California that's used that scans the horizon looking for smoke, and we've developed algorithms that look for smoke to differentiate between haze and things like that, and we have a very high accuracy rate on that. So that's one particular application where machine learning has been applied to scanning the horizon for smoke.
So I don't have any more here. Does anybody in the audience have any more questions for our panelists? We probably have time for one. All right, do you want to give some closing thoughts? Anything you wanted to talk about that we didn't get to?
Yeah, the way I look at this technology is it's coming at us. We can take advantage of this. We can figure out how to use it effectively, but it's coming. So we can be on the bus, driving the bus, or we can be dragged behind the bus. One way or another, we're going to be using it. So,
yeah. And to piggyback on that, it almost goes back to what is our role in the larger AI ecosystem. There may be none of us that are AI experts, but if we want to use this intelligently in our systems and to leverage all the benefits of AI systems, it may require many of us stepping outside of our comfort zones to lead efforts within our own groups or agencies or companies or whatever it may be, to develop a strategy, to develop a community practice, to do some things and stretch where you may be uncomfortable. I'm used to being a geospatial expert. I am not used to talking about AI. But if we're going to move the ball forward, we have to stretch a little bit.
And I guess just to piggyback on that, living in the cybersecurity side, enabling technology side, it's moving fast. Technology is moving so fast these days. I actually was in a meeting a couple of weeks ago, and our deputy administrator said to the CIO, "You need to get comfortable with feeling uncomfortable." Things are moving fast. I think to tie back to Everett's point around you're either going to get hit by the bus or dragged by the bus, and if we're not keeping up with the pace, then we're going to get left behind.
So one of the things that I'm really interested in seeing, and I think may manifest, is at the intersection of LLMs and geospatial data, the expansion of spatial thinkers and geospatial users. Now, Esri simplified the GIS to a point where you didn't have to have a degree in geography or a technical discipline to be able to use a GIS. Web maps have taken it even farther, but if you can enter language into a chat client and have that chat client return to you the results of some spatial SQL operation behind the scenes, and you didn't necessarily you were not thinking in SQL, but you're thinking in, I want to understand what's going on around this area. It opens up a whole new audience and a whole new set of practitioners in the geospatial space. And so, with great power comes great responsibility, and we all know the adage of buttonology and a lack of the fundamentals when it comes to some GIS users. And so I think it's going to be important for us to help expand the knowledge and understand the ramifications of doing geospatial operations. But it's exciting to see that these tools may open the aperture and usability of geospatial information that much more.
Great. Well, thank Thank you, everybody. We're at time here. Just quickly, Element 84 has an AI ML geospatial workshop coming up on the 15th. I can give you more information about that if you want to come see me, but please join me in thanking our panelists for being up here and for this great discussion.